Hi everyone, myself SreeVishnu and my friends Aryan, Mitra and Madhumitha. So we are a team of four from Jain University and today we are excited to present the outcome of our internship project. So our project is titled as Microcontroller Based Washing Machine Simulation using Pixim Lab. And internship overview. So this project mainly focused on embedded C programming and microcontroller concepts. And this was a 1 month intensive training combining theory and hands-on practice. It was developed simulation, which was based on embedded application using virtual boards. And it was emphasized real-time system behavior. Example as the project named as washing machine control logic. And, and this includes individual ownership of the project from design to implementation, and it encouraged debugging, rapid prototyping, and problem solving in embedded systems. And the goals of this internship is it strengthened our foundational understanding of embedded systems by exploring core components like microcontrollers, memory, and input-output handling, and applied embedded C programming to implement real-time control logic for practical applications. And it also helped us gain in-depth knowledge of timers, interrupts, and peripheral interfacing to build responsive and efficient embedded systems. Its design and we developed a fully simulated project that mimics the behavior of real embedded device using virtual tools. And we got a hands-on experience with development environments like MPLab 10 IDE and Pixim Lab for coding, simulation, and debugging. And also it enhanced technical presentation and documentation skills by preparing reports and explaining the project flow effectively. What we learned in this internship was we learned embedded C with register level coding, which created modular source and header files for readability and debugging. We interface CLCD, keypad, buzzer, and a fan using GPIO control and managed input output through TrisX and PortX configuration. And we also configure timer 2 and use delay for countdowns and animations during washing cycle execution. We implemented a finite state mission for smooth UI transition between idle, selection, execution, and pause states. We also debugged the entire simulation using Pixim Lab by tracing logic, peripheral response, and display outputs. And we also solved practical challenges like debounce, screen formatting, and pause or resume logic using efficient code handling. Embedded system. So embedded system combines both hardware and software to perform a dedicated function within a larger system. These are real-time and reactive, which is designed to respond immediately to specific inputs or events. And common application include washing machine, microwave ovens, printers, automotive systems, and industrial machines. These systems are known for their small memory footprint, lower power consumption, higher reliability, and it's typically built around a microcontroller for integrating CPU, memory, and peripherals on a single chip. The key concepts includes interrupt service routines, polling mechanisms, and direct register level programming for precise control. Introduction to PIC 16 F877A. So it is a 40-pin 8-bit microcontroller which is widely used in embedded system. Ports A to E provide digital input-output lines for peripheral connections. It features built-in timers, EEPROM, and ADC for versatile functionality, and it operates at up to 20 megahertz clock frequency for reliable and real-time performance. And the programs are developed using MPLab 10 IDE and XC8 compiler, and it's most commonly used in industrial, consumer, and educational projects. Tools and environments. So the first tool which we used is MPLab 10 IDE, which was used to integrate development environment, which is used to write, compile, and debug embedded C programs for PIC microcontrollers. XC8 compiler, which converts C code into machine level X files, which is compatible with PIC microcontrollers. Then Pixim Lab, a virtual simulation tool that mimics the behavior of hardware components, allowing testing without physical devices. Virtual peripherals used is CLCD, which is nothing but character LCD, buzzer, fan, LED, and a keypad. which is all simulated through the Pixim Lab environment. So character LCD functions which were used were CLCD print and CLCD put. CLCD print is for printing a string on the LCD, and CLCD patch is for single character at a specific position. Then modular programming structure. We used main.c which contains the core logic and the function calls. CLCD.c which handles the LCD display control. Keypad.c which manages keypad scanning and input handling.
So myself, Aryan, and I'll be talking about the project objective. So our main goal was to create a real-time environment of a washing machine with the help of MPLab and the XE8 compiler and PixSimLab interface. And our main goal was to implement the core washing machine cycles such as wash, rinse, and spin that is most common in any washing machine. And it also includes a support for door open detection, like when you open the door and the washing machine tends to turn off automatically for safety reasons and cannot be running on when even though the lid is open. So we use a CLCD screen such as for displaying the washing paused, spin complete, etc., etc. With the help of, I mean, the CLCD screen helps us to display what particular working is happening in the machine. So the entire system is interactive and a keypad driven, eliminating the new need of external hardware buttons. So the project requirements are, so we have used the inputs that is switch 1 to switch 6. These are used for the input for selecting washing modes, water levels and controlling functions like start, pause or reset. See, the outputs are used with the help of CLCD, buzzer, and a fan. So the LCD displays the characters and the rest of the things for displaying for the user to know what particular operation is going on. And the buzzer is used to notify if the particular functions or the working is over. And the fan is in the form of a motor that is used to simulate or relate to a real life washing machine motor. So here we're using a fan to display what is the working of the motor. And the microcontroller unit which we are using, as my friend told Vishnu, is we are using a PIC16F877A as a 40-pin 8-bit controller that supports timers, interrupts, and a sufficient I/O for simulation. So, the simulation board is a PIC Genius, is nothing but a developer board that is used in PixSim Lab. It's a hardware board as well, which we get in real life as well. The interrupts and timers are used to manage real-time behavior such as timing, wash, spin durations. It's timers and interrupts are of different types. Like just like delays in other controllers, these are interrupts and timers that are used in PIC. And clear state management. Uh, this system follows a well-defined state machine model to switch between modes, like ideal for smooth control flow and logic clarity. So this is the block diagram of how it works. So power on is using switch 5, pause stop, switch 6, navigation, switch 4, door status, switch 1, display, washing status, CLCD and buzzer and the motors. These are all the output devices on the right side and all the input devices on the left side. So left side is a keypad and the right side is all the other devices. So power on screen, the user is prompted to press key 5 to turn on the screen. And once pressed, the power on animation is triggered and then once pressed, the power on animation is triggered and to simulate system boot visually. A progress bar is created using CLCD puts to fill the top and bottom lines of the CLCD. And after the animation, the buzzer can be activated during a power on to provide audio feedback to the user. A short delay of 500 milliseconds is used for the animation to enhance realism. So this is how the power on screen output would be. So the washing machine program menu, the system includes 12 predefined washing programs such as daily, heavy, delicates, quick wash, woolens, and more. The program selection is user-friendly and designed to mimic real washing machine interfaces. So switch 4, short press is used to navigate through the menu. Switch 3 at the time on the CLCD. Switch 4, long press confirms the user selection. And the CLCD shows 3 programs at a time, giving a compact view of available options. And the currently selected program is indicated with an asterisk, making the UI intuitive and easy to follow. So this is how the washing programs menu output would be.
Myself, Mitra, I would like to continue with the explanation of the working of the washing machine. So let's start off with water level menu. The water level menu offers five options, which is auto, low, medium, high, and maximum levels. These represent the amount of water to be used in the selected washing machine program. Navigation uses the same logic as the program menu with switch 4 to scroll and switch 5 to select. The selected index is stored in a variable and later it is used to determine washing duration. The selection process is handled using the navigate menu function in the code. The CLCD updates instantly as the user scrolls through options, enhancing interactivity. Circular scroll logic is implemented to loop back from last to first item seamlessly. This provides a smooth user experience and avoids boundary errors during selection. So this is the water level menu output that we have gotten. It displays the three water levels, auto, low, and medium. Next, let's focus on start screen. It displays a prompt to the user. Press start using switch 5 to begin or set using switch 6 to modify settings. Pressing set, that is switch 6, allows the user to re-enter the program and water level selection menu to make changes if needed. Pressing start, that is switch 5, proceeds to the main screen showing the chosen program and the estimated time on the CLCD. A short delay is added before switching to the function screen, simulating a real washing machine startup behavior. The entire control flow is managed using clear if else logic, ensuring that user inputs lead to correct transitions. Key presses are immediately recognized and acted upon, giving a smooth and responsive user experience. So here's the output of this start screen. So according to the switches we press, that is switch 5 leads to start and switch 6 leads to stop. Next is function screen overview. The total washing time is divided equally into three sequential phases: wash, rinse, and spin. Each phase runs for one-third of the selected program duration using countdown logic. The CLCD continuously displays the current phase and remaining time during execution. This provides real-time feedback to the user through the washing process. If switch 1 is pressed, the system detects a door open conditions and triggers a warning. The process is paused, the fan is turned off, and the CLCD displays door open. Pause and this process is paused, the fan is turned off, and the CLCD displays door open. Pause and resume functionality is managed by switch 6, pause or exit, and switch 5, resume. This adds user control for interruptions during the washing operation. The fan simulated motor is turned on during each phase using the fan equal to one command. At the end of each phase, the buzzer is activated to indicate the transition to the next stage. So this is the function screen overview output. The function wash and the time is set. The 5 leads to start and 6 leads to pause. Next is phase wise execution. The washing cycle is divided into three main phases. Phase 1 wash simulates detergent mixing and agitation. Phase 2 rinse simulates water rinsing to remove detergent. Phase 3 spin simulates spinning to dry the clothes. Each phase runs for a preset time, example 3 seconds. During simulation for demonstration purposes, the CLCD is updated every second, showing the current phase and remaining time, creating a real-time feel. A virtual fan motor is toggled on or off by a port C, indicating activity during washing and spinning. This time-based execution is managed using timers and delays, giving the impression of real appliance behavior. Proper phase transition logic ensures smooth flow from wash to rinse to spin, maintaining cycle accuracy.
Hi, I'm Madhumitha. I'll be continuing the presentation of washing machine simulation, door open logic. Pressing switch 1 simulates the door being opened during the washing operation. This triggers the system to immediately pause the ongoing phase for safety, and then the buzzer is turned on to alert the user. And this audio feedback ensures the issue is noticed promptly. And then the CLCD displays a warning message, door open, please close. This message will remain until the door is safely closed by releasing switch 1. The system enters a wait loop and does not resume automatically. Only once the door is closed does the process continue to the next countdown cycle. And this it ensures user awareness and safe operation during the active washing phases. And this is the output of door open logic. Pause and resume logic. Pressing switch 6 during any washing phase triggers the pause mode in the system. The ongoing operation halts immediately, allowing the user to intervene safely. The fan is then turned off as soon as the machine enters the pause state. This simulates the motor stopping just like in real world washing machines. The CLCD displays the message machine paused with instructions for next steps. This ensures the user knows they are in controlled pause state. Pressing switch 5 while paused resumes the operation from where it left off. This allows seamless continuation without restarting the full process. Then pressing switch again during the pause triggers an exit from the current cycle. This system resets all selections and then returns control to the start screen function. Timer handling. Timer 2 is initialized using init timer 2 to enable precise time tracking for managing different system functions. A dedicated interrupt service routine is triggered by timer 2, acting as a real-time delay loop without blocking the main program execution. This setup ensures accurate timing between each cycle phase, wash, rinse, and spin, maintaining simulation realism. The delay ms function is used to add short delays, mainly for CLCD transition effects like blinking or loading messages. Then the buzzers alerts are triggered with a short software delay loop, giving immediate feedback when the keys are pressed or cycles complete. Fan, which is a motor control, is tightly synchronized with each washing phase using the timer and port logic, ensuring it activates only during required operations. CLCD display management. The CLCD print function is used to display strings of text such as prompts, instructions, and status messages. And CLCD patch function is used to place individual characters at specific coordinates on the CLCD, useful for symbols, timers, or highlights. All four lines of the CLCD are effectively used to show menus, user instructions, phase updates, and selected options. Text is center aligned wherever possible for a clean and user friendly interface, enhancing readability. It provides a visual feedback throughout the process, such as blinking text, asterisks for selection, and countdown timers to simulate real device behavior. The display is dynamically updated during each phase, ensuring the user is always aware of what the system is doing in the real time. Final completion screen. After all three phases complete, the CLCD shows message program complete. The second line displays remove clothes to indicate the wash cycle is finished. The fan is turned off as the machine completes its operation. The buzzer is turned on briefly to alert the users the program has ended. The screen remains static with the final message until the system is manually reset. This gives the user time to act and ensures the machine remains in the safe state. The a while loop is used to hold the system in an idle state after completion. This loop prevents unintended resets and clearly signals the end of the project execution. This is the final completion screen output where we can see the output declaration of program completed and telling the users to remove the clothes.
So I am Aryan again. So I'll be talking about the first program. So that will be nothing but so we've used the CLCD dot header. So all the headers are attached to it. So that is the CLCD, the digital keypad, the fan dot h, the timers dot h. So these are the required headers files. So the LCD screen, all the headers are required. And then the source files contain the clcd.c that contains all the predefined ports for the LCD. The digital keypad.c contains all the predefined ports for the keypad that is used for the inputs. So here the inputs are the mainly the keypad. The outputs are the LCD, the fan and the buzzer, and also the mainly the CLCD fan buzzer and the timers are used here for giving delays between each other, and here the main.c mainly contains all the main programs. So here we can see the constant char, which gives us all the particular programs that has daily, heavy, delicates, white, stain wash, eco cottons, woolens, bed sheets, rinse and dry, dry only, wash only, and aqua store. So these are the number of programs. And after that, we have the number of water levels, that is auto, low, medium, high, and max, and also the functions into the water levels, that is wash, rinse, and spin. So according to that particular thing, it is programmed to wash, rinse, and spin in a particular duration depending on the program selected. So here we've used the mainly we are from the Emertxe interns batch it. So we've displayed that. So this is the main.c program. Onto the simulation. So here we load the file onto my friend Mitra.
Hi, yeah, so I would like to explain a little part of simulation. So, as we saw earlier, there will be a display called as Emertxe Interns Batch 8, after which pressing key 5 will power on the washing machine system. So here we're using PIC 16F8 778 development board. So as we press key 5, there will be powering on of the washing machine.
So hi, I'm Madhumitha. I'll be speaking about washing program menu. So this is the washing program menu where you can see daily, heavy and delicates. So when we press RB3, so the menu change, like you can, the choosing the option changes after you press that button.
Hi, this is myself Vishnu. So I'll be speaking about the water level menu. So pressing RB4 will let us go to, tell the water level options. RB3 to scroll the options, which is auto, low, mid, high. And RB4, after pressing RB4, it will be selecting the water level required.
So after we select RB4, we have an option for start and set. So when I start RB5, RB4, sorry. So we'll have an option where it all automatically starts, and then the function wash starts for particular duration. Then we'll have wash, rinse, and spin for 3 durations for the particular 50 seconds, depending on the program selected. And then yeah, the buzzer sound cannot be heard because of the because of the app which you've used for recording. But the buzzer will turn on uh, after the particular working of the function gets over. So the program completed, and you can remove clothes. Same like that, there'll be multiple options which can be used. So basically, that's the full working of the simulation.
Key learnings. We have gained hands-on experience in embedded system project development from idea to execution using simulation tools. Learn to implement real-time logic using interrupts and timers, ensuring timely execution of tasks like phase changes and input handling. We understood how to effectively use peripherals like CLCD, fan, LED, and buzzer to create responsive and user-friendly interface. Applied state machine design in embedded C, organizing code into logical states like idle, washing, paused, and completed for smooth control flow. Became proficient in debugging and testing using a virtual simulation environment without needing physical hardware. Followed modular programming practices by splitting code into clean, reusable files. Like example, main.c, clcd.c, keypad.c, improving readability and maintainability. Conclusion and acknowledgement. We successfully developed a complete washing machine simulation using PIC microcontroller and embedded C, simulated all phases, input handling and outputs in real time with accurate logic and display, gained hands-on experience in microcontroller programming and peripheral interfacing techniques, worked with keypad inputs, CLCD display, buzzer, and fan control using register level access, dependent understanding of embedded system designs, timers, interrupts, and finite state machines, applied simulation tools effectively to build, debug, and validate the system without hardware. Heartfelt thanks to Emertxe mentors and instructors for their guidance, support, and feedback. Special appreciation to the project coordinators and technical staff for making this learning smooth. Thank you. Thank you.
Thank you.
Thank you.
Thank you.